Dear students, today our purpose of this lecture is to analyze the voltage sources when they are connected in series, to analyze the current sources when they are connected in parallel, and to analyze the total resistance across two terminals when a number of resistances are connected in series and or parallel, right? So this particular lecture covers the voltage sources in series and current sources in parallel, and then we have resistances connected in series and parallel. As we have already discussed that the voltage sources are those electrical sources or energy sources which provide voltage to the circuit. Now we are discussing the DC sources here, and we intend to understand the fact that what happens when two or more sources, what happens when two or more sources are connected. I'm talking about voltage sources basically, connected in series to one another. So this is the question. Now the answer to this question is that when you connect the voltage sources in series with one another, so there are certain ways how the voltage sources are connected. So let us take one example here, and it is also shown in the diagrams here with an example, right? Let us say you have a voltage source V1 and you have a voltage source V2. Now you can ask one question, that why these voltage sources are connected in series? Because we all know that when voltage sources are connected in parallel to one another, uh, across the two terminals, the voltage shall remain same, right? So they have to be connected in series basically, and also as we know that the voltage sources ideally have zero resistance, or you can say practically also they have negligible resistance. So in that case also, if you connect a voltage source in parallel to a current source, in parallel to another voltage source, so there may be a case that, let us say if it is a 20 volt and if it is a 10 volt, so the current can short here, because theoretically this particular voltage source is offering kind of zero resistance, right? So, and also it is not intended, and it is not good idea to connect the voltage sources in parallel to one another, right? Okay, so there are certain consequences of this. So, and we also know one fact that the voltage is when there are certain elements which are connected in series to one another, the voltage is divided in series basically. Okay, current remains same through each and every element, right? So now if we talk about two voltage sources, which are connected, so there may be two possibilities here, right? So, so there are two terminals, and these two terminals are, let us say, A and B, and these are the load terminals, let us say. Okay. Now this is V1 and this is V2, and if this is positive, this is negative. Not if, basically this is positive, long leg is positive and short leg is negative. This is positive and this is negative. Now the direction of voltage is this. So in both cases, if you see, the direction of voltage is same, right? The direction of voltage is same, right? So the total voltage here can be, means these two voltages which are connected in series can be replaced with a single voltage source which is equal to V1 plus V2. Now, how did I add these two voltages? Because I have seen that the direction of these two voltages is same. That means these two voltages, these voltage sources are aiding each other, right? They are not opposing. Like in this example, if you see, there is a voltage source of the 10 volt and there is another voltage source of 10 volt. Now, the direction of their voltage is same. It is like this, right? So, the total voltage, if you will connect a voltmeter here, this voltmeter shall measure 15 volt. This volt, if you connect a voltmeter here, this voltmeter will measure V1 plus V2 in general, right? Now, if in second case, if we take a second case, wherein the voltage sources which are connected are not in same direction, means their polarity is not in same direction. In that case, what will happen? For example, if you have a voltage source, okay, with positive terminal and negative terminal, and then you have another voltage source connected in the same path which is coming in series to, let us say this is V1 and this is V2, wherein V2 is coming in series with V1, right? So it is positive and it is negative. So when you will connect a voltmeter here, let us say these two are the terminals, let us say these are load terminals, for example. Now, if you connect a voltmeter here, this voltmeter will give you the total voltage or net voltage. In fact, I won't use the word total voltage, net voltage. So the net voltage would be the algebraic sum of these two voltages. Now, when we say algebraic sum, we note the direction or polarity of the sources, right? So what will be the net voltage here? It would be V1 minus V2. It could be or V2 minus V1. Okay, so that depends upon the magnitude and strength of the voltage source also, right? So it would be the difference in any way. It would be the difference of two voltages. Okay, because these two voltages, because these two voltage sources are opposing each other, right? They are opposing each other. Like in this example, if you see, one voltage source is of 10 volt, another voltage source is of 5 volt. They are opposing one another, means their direction is not same. So its direction is in this way, this side, and you see it is in this direction. The voltage is in this direction, right? So the net voltage, when you connect a voltmeter here, or you apply the network rule here, so you will get the voltage equal to 5 volt, means the difference of these two voltages. Okay, so the summary or the conclusion of this point of this fact is that when you have the voltage sources connected in series, okay, so let us summarize this one. So to summarize, when you have the voltage sources connected in series, so net voltage would be across the two terminals, basically net voltage across the two terminals of that branch in which you have the voltage sources connected in series will be the net voltage. I won't use the word total voltage. The net voltage will be the algebraic sum of all the voltage sources connected in that branch, right? Okay, so the whole story is mentioned here in these lines, you can read. Now let us come to the current sources in parallel. Now there may be a question arise that why do we have current sources in parallel and why don't we have the current sources connected in series? Okay, so it is undesirable to connect the current sources in series to one another. There are certain reasons behind it. So second, reason is that we know that when we have, let us say, a current source connected here and or a voltage source basically, and we have some pure parallel branches. Okay, so we know that current is divided into all the branches, right? It is divided. Okay, so current remains same in series, voltage remains same in parallel, right? Okay, so it is intended, okay, it is intended and it is desirable. If you have the current sources connected in parallel, you can algebraically add them. Now, when we use the word algebraic, we actually also considering the direction of the arrow of the current source. We all know that the direction of the symbol of current source is this, an arrow encircled, right? Okay, so it may have upward arrow direction, it may have downward arrow direction. So this arrow indicates the direction of flow of current, right? Now, so we need to consider the direction also. Okay, so just a minute. Now, so let us see that we have a network. We have a network in which we have two or more than two current sources which are connected in pure parallel to one another. Now, when I say pure parallel, what I mean to say actually is that they should share the same junction. Okay, they should share the same junctions. Means all the junctions to which the current sources are connected must be on the same potential. For example, there is a current source, there is another current source. Let us say this is I1, this is, let us say, I2, and then there is one more current source. Let us take its arrow downward, and it is, let us say, I3. Then you have one more current source, and its arrow is, let us say, again upward, and it is I4. Then what would be, let us say there is a load resistance connected, right? So what would be the current in this particular load resistance? Let us say this is current I. So I would be equal to I1 plus I2 minus I3 plus I4. That means you can replace all these current sources with one single current source across these two terminals AB, right? So these two terminals will remain as it is, A and B, and this is the load resistance here. And now, will we take the direction of current upward in this case or downward? I have not drawn the direction of arrow inside this circle as of now. Why? Because I would see whether the algebraic sum, this is an algebraic sum, they are algebraically added because I have considered the directions, right? So, whether this is a positive value, I'm sorry, this is a positive value or negative value. If it is a positive value, then we will take upward direction. If it is a negative value, we will take downward direction. However, there is no thumb rule to take upward direction for positive and downward direction for negative. There is no thumb rule. It is totally in relation to one another. If I am taking the upward direction as positive, so obviously the downward direction will be negative with respect to this upward direction. So if my all this is a positive value, I will take the upward direction here. So that means I have replaced all these current sources with a single current source. So this technique can be used to simplify the networks. If you see that some current sources are falling in parallel to one another. Now, when I say parallel, I mean to say they are sharing the same junction. Okay, they all are sharing same junction because all these nodes, this one, this one, this one, all these nodes are at same potential. Why they are at same potential? Because because they do not have any voltage drop in between. They are short. They are short. Right? Now let us understand this difference with one another example. Let us understand this difference with one another example. Okay, in that example, I will take one circuit in which we have some current sources connected in parallel, but there is one special case in this. Okay, so let us take one. There is one source, let us say its direction is upward, and there is one more source whose direction is again upward. Let us say this is, let us say, I1, and this is, let us say, I2. Then you have a resistance here. Okay, then you have a resistance, let us say, and then you have one more, current source here, and then you have one, let us say, for simplicity, I'll take all the directions upward. I hope it is clear to you that when to take negative and when to take positive, right? For upward, you can take positive. For downward, you can take negative. However, there is no thumb rule. It is totally up to you. Okay, you can take any direction, any arrow as positive or negative. It is totally up to you. So this is some resistance. Let us say its values are small r, as for example, right? So there is last we have, let us say, a resistance which is a load resistance RL. This is I1, I2, let us say this is I3, and this is I4. Now, dear students, I1 and I2 are in parallel to one another because they are sharing the same junction, same node, right? These two nodes are at same potential, so they are sharing the same node. But the combination of these the two sources and the sum of these two sources, because they are also sharing the same, uh, what do you say, node or junction, right? These two nodes are at same potential, but all these four nodes, let us say it is A, B, C, and D. Here A and B are at same voltage. C and D are at same voltage, but AB and CD, sorry, not this one. AB and CD, they are separate. They are separate because they have a resistance falling in between, and this resistance is causing a voltage drop between B and C. This resistance is causing a voltage drop between B and C, and that is why you cannot add I1, I2, I3, and I4 all together. You cannot add. Okay, so in that case, what you will do, you'll replace this network with a single network wherein you have a current source. Let us say it is upward because both are upward, so it is equal to I1 plus I2. Then you have a resistance here. Then you have another current source, dear students. Value is I3 plus I4. And then you have the load resistance here, R, like this. Like this you can add, but you cannot add these two because these two are not sharing the same node. Okay, because of this resistance which is falling. So this is what I wanted you to understand, that what is a pure parallel and what is not a pure parallel circuit, right? So all the currents would be in parallel to one another when they are sharing the same node. Means the node to which they are connected is at same potentials, right? Then you can consider them. Okay, so let us understand with the examples as shown in the diagrams below. In the first diagrams, as you can see, there are two current sources. Okay, so they have the same direction, upward, and the net current that would be flowing in these terminals, if it is a load connected here, so this load will have 10 ampere of the current, right? Now in the second case, if you see, if it is a load, so since the direction is opposite to one another and they are sharing the same node, because these two nodes, they do not have any resistance connected in between, and hence these two nodes are at same potential, this one and this one. So these two current sources are parallel to one another, right? But since they are opposite to one another and their value is also same, so you would say that the current here is zero, right? The current here is 0 ampere, right? Now let us take this example here. Here we have two sources which are in parallel, or you can say anti-parallel to one another, right? And one is 5 ampere source, one is 3 ampere source, right? So the net current that would flow in these terminals, let us say if load is connected here, would be 2 ampere. Okay, would be 2 ampere. So these two, so the summary of this particular fact or concept is that if you see a number of current sources connected in parallel to one another, you can replace all those current sources with a single current source whose value is the algebraic sum of all the current sources which are connected in parallel. All right. So this was about current sources. Okay, now let us come here. Now resistance is in series. Okay, so this is what you have studied in your school also, right? So okay, now if you if you have resistances connected in series across any two terminals, okay, let us say there are terminal wherein we have one resistance, then we have another resistance, then we have another resistance, and let us say these three resistances are connected in series with one another across these two terminals A and B. So what would be the equivalent resistance of this circuit across these terminals A and B, right? This is the purpose of this particular concept. Okay, now when do we call that the resistances are connected in series? When all the elements share same current. If all the elements connected in a branch share same current, we say that these elements are in series. For example, if you have a circuit like this, you have a voltage source, you have a voltage source, you have a resistance here, you have a resistance here, you have one more resistance, and then you have a resistance, and then you have a resistance here like this. So this is one network. just to understand the concept, this is, let us say, VDC, and this is, let us say, R1 and R2 and R3 and R4 and R5. Now, when the current would start flowing from this particular source, it would reach to this junction. I hope what is junction, that is clear to you. Junction is a point in electrical circuits where three and more than three branches are connected. So we have three branches here, 1, 2, and 3. So this current would divide in this branch and this branch depending upon the branch resistance, right? Now this current will flow through R3. The same current would flow through R4, the same current will flow through R5, and from here another current is coming. These two current will meet at the junction and you have the same current here. Okay. Now, because this R3, R4 and R5 are sharing the same current, so we will call that these three resistance are in series, right? Now the purpose is to understand what would be the equivalent resistance across any two terminals if n number of resistances are connected in series. Okay. To understand this, we have a circuit as shown here, which has a voltage source. Then you have R1, R2, and R3 resistances. So these three resistances, which are connected in series, can be replaced with a single resistance Rs. What will be the value of Rs then? What will be the value of Rs? This is what we will understand. Now we know that when the current will flow through R1 as shown in the diagram, when this current I will flow through R1, it will have a voltage as per the sign convention. It will have a voltage drop V1 here. Then the same current I1 will flow here through R2. It will have again a voltage drop V2 here. And the same current is flowing through R3. So there would be some voltage drop, let us say V3 here. And then the same current is flowing like this. Okay, so what is V1? V1 is equal to IR1. What is V2? V2 is equal to IR2. What is V3? V3 is equal to IR3. Now we know that in series, the applied voltage is divided across each element. We know that in a series circuit, the applied voltage is divided across each element, right? So that means V is equal to V1 plus V2 plus V3. Okay, I'm sorry. So V is equal to V1 plus V2 plus V3, right? So we can replace V1. So we can replace V1 with IR1, V2 with IR2, and V3 with IR3. So taking this I as common, you have R1 plus R2 plus R3 V. So taking I on the other side, you have V by I, R1 plus R2 plus R3. As per Ohm's law, V by I is equal to R. So let us take it as Rs because the resistance is on series. So Rs is equal to R1 plus R2 plus R3. That means if you have resistances connected in series, so the total resistance across the input terminals, which we also call as equivalent resistance, okay, so the total resistance is equal to the sum of each resistance. Sum of each resistance, right? So if there are n number of resistances connected in series, R1, R2, R3 dot 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 dot, then Rn. So this is R1, this is R2, this is R3, this is Rn, and the current is I here, and the voltage is, let us say, V. So across these two terminals A and B, the total resistance R is equal to R1 plus R2 plus R, right? Similarly, we have resistances connected in parallel also. So when do we say that the resistances are connected in parallel? When they are connected across the same node. Like in this diagram, if you see this node, this node is, let us say, A and B and C and D. So because these two nodes do not have any resistance in the path, so these two nodes are said to be at the same potential. These two nodes are also at the same potential. These two nodes are also at the same potential. So all these nodes here in this case are at same potential. So these all nodes are one node, right? Okay. So then you can say that the resistances are parallel, or you can say that when the applied voltage is same across each element. So all the elements are in parallel to one another, right? Now what will be the equivalent resistance in this case? That is the purpose. So let us consider one circuit here. So in this circuit you have a voltage and a resistance R1, R2, R3 which are connected in parallel to one another. You can replace all these three resistances with a single resistance Rp, where P indicates parallel. Okay, we all know that when this current I would flow, when this current I will flow here, this current I will flow, it will come to this junction, it will divide here in this junction and go to this particular junction. Now this is, let us say, node A, and this is, let us say, node B, for example. So these two nodes are at same potential. So this current will divide into this particular path and this particular path. So this is, let us say, I1, this is, let us say, I2, and this is, let us say, I3. So these three currents are basically nothing but this current. Okay. So I is equal to I1 plus I2 plus I3. Now if we replace, we know that I1, if you go to this particular diagram here, now what is I1? What is I1? I1 is equal to the voltage across this resistance R1. I1 is equal to the voltage across this resistance R1, which is nothing but V, because same voltage is appearing across this resistance also. Okay, so it is V by R1. What is I2? What is I2? I2 is the current flowing in R2, which is equal to the voltage across R2. The same voltage is appearing, right? So it is V by R2, and then you have I3 is equal to V by R3. Now if you add and replace here, you'll get the similar kind of expression. Like here, taking V as common, you have this one by R1 plus 1 by R2 and 1 by R3. Now taking V on the other side, which is I by V, which we also call as conductance, right? Right. So which is equal to 1 by R1, 1 by R2, 1 by R3. Okay. So but we know that V by I is equal to Rp. Okay, if you go back to this particular circuit here, if I is the current flowing in this particular circuit, what will be the value of I? I is equal to the applied voltage V divided by the resistance Rp. Now what is Rp here? Rp is the sum of these three, not sum, basically combination of these three resistances, right? Now, the same is the case here, you can see. So Rp is equal to V by I, or 1 by Rp is equal to I by V. So you have replaced it here. So you have the parallel combination of the resistances. Similarly, if you have n resistances connected in pure parallel to one another, so you have the net, resistance across the input terminals equal to this expression given by this equation. Okay, so this is about the parallel combination, right? Now, as you can see in this, GIF diagram, these resistances are in series, guys. So they are sharing the same current, right? The same current is flowing here in this loop, right? And here, if you see, these three resistances are in parallel to one another. So this particular current which is flowing here is dividing at this particular junction, going in these three branches. Now the value of I1, I2 and I3 depends upon, it is V by R1. So V is constant, all three resistances, right? Hence, I1 is inversely proportional to R1. So similarly, I2 is equal to V by R2, I3 is equal to V by R3. Hence, we can say that the current in each branch depend upon the resistance here, right? You can understand this with one more animated picture. As you can see, the current is flowing in one direction here, right? So the current here is flowing in one direction, and that because it is a DC source, okay, DC source. So it is a unidirectional, right? Now here, if you see, the current is dividing in this branch and this branch. The same current is flowing, the current is dividing and then meeting at this particular junction. The current is dividing, meeting at this particular junction. You can also notice one more thing, guys, that here the value of resistance is 2.5, value of resistance is 400 ohm. This is 400 ohm. So the equal current is dividing both the branches, equal current. Now, if you see the second picture, in the second picture, this resistance here, this one is 400 ohm, this is also 400 ohm. So 5 milliampere of current is flowing because of this 1 volt source. So equal current is flowing. But now you have increased the value of resistance here and you have decreased the value of resistance here. Now what is happening? The current in this branch has increased and the current in this particular branch, you can see, is decreased. So this indicates that current always flow more in that branch which has minimum resistance, right? So the summary of this lecture is that we have understood that the voltage sources can be connected in series. They can be helping each other, means they can be added, they can be algebraically added, they can be subtracted, right? Similarly, current sources can be connected in parallel to one another. If you have number of current sources connected in parallel, all those current sources can be replaced by a single current source, and then you have resistances in series and parallel. So thank you so much.